And this would lump very nicely into relativity. But we'll put that on hold for a bit while we get into inductors, so some of the more practical stuff. Questions about the magniforious nature of what we just did? Yeah, I know, you're awestruck. All right, so chapter 33.
That was all on chapter 34.
We started out at chapter 30 thing, and then chapter 32 thing, and then a 34 thing, now back to 33. It comes down to, there's a logical way that I would present it, there's a logical way that she presented it, and we're just a little bit out of sync here. All right, what do I have here? All right. And if I run a current through it, what's going to happen?
The magnetic field change in magnetic flux?
When it first starts, there'd be a change in the magnetic flux. Once a current gets going, there's not a change in the magnetic flux. But as if we start with nothing, if this is just hooked to, I'm going to put a switch in there. When I close the switch, I'm going from no current to current, so I will be creating, how am I changing the magnetic flux?
By moving current. By moving current, you induce a magnetic field.
Okay. And what is the magnetic field in the middle of the solenoid? Looking for a formula. We did derive this last time. Magnetic field from a solenoid with a current I.
Use of not in
Lowercase n. Where lowercase n is the linear density, coil density. So that's mu sub naught times the number of coils per unit length times I. I am using a lowercase l here on purpose. We will be using a capital L at some point during this, so please use a lowercase l in your notes, or something other than a capital L.
capital N is the number of coils.
Say it again?
You say capital N is the number of coils.
Capital N is the number of coils. So you just count up the coils, divide by whatever the actual length is. Now, if I am changing the magnetic flux though, because when I first switched this on, again, I'm going from no current to current, so my magnetic field goes from nothing to this. During that transition, my magnetic flux changes, so what else must be happening?
Change in electric field.
Which causes what?
Change in the magnetic flux.
Okay. Is it going to, all right, so I change in an electric field, in essence, I create this voltage, cutting down to simpler words, I don't want it, which creates a secondary current. So I have this current that is created by the battery, and then I have a secondary current created by my change in the magnetic flux caused by the change in the magnetic field. I want to keep it as just voltage. Yeah, keep it as voltage. Negative. Now, what we had before was the integral around some loop of E dot dl, which is where Austin was coming from with the change in the electric field. But voltage is really the key part I want to look at. Now, the secondary current opposes the initial current. If it were the same, in the same direction as the external current, from the primary current, I should say, if it's the same direction, that means that my change in magnetic field would get a current that helps make it even bigger, which would then, it would be a runaway process, and eventually it would burn out, heat up, explode, depending on what's around at the time. And so I want to figure out what is the voltage created by turning this thing on. And so this is negative dVA dt. Now my area is constant here. The magnetic field, we're pretending the magnetic field is constant within the solenoid. In reality, it's not 100% constant, but we are assuming that it's large enough. It's an ideal solenoid. So let's throw that in there just for a little CYA. All right. So the area, what area are we talking about here? And if you need the visual, what area are we talking about?
Cross-sectional area?
Of?
Magnetic field.
The coils?
Where the magnetic field crosses the cross-section.
Right, okay, yeah. It's not of the cross-sectional area of the wire, it's cross-sectional area of the hole.
Okay.
I assume that's where you two will go. Yes, sure.
I was going for the coils, but.
Well, I view the coil as this, and so
Yeah,
it would
okay.
be that
Gotcha.
area there. In the electromagnetic induction lab, that becomes probably the biggest issue or biggest point of error in the calculations in that lab is when confusing the cross-sectional area of the wire and the cross-sectional area of the hole. It's the cross-sectional area of the hole. So, but we've got to be careful here. And some books, actually most books, do this a little bit differently. Instead of having B times A right there, they acknowledge that I got a whole lot of A. Every single one of these coils has its own cross-sectional area that the magnetic field is going through. So technically, times N. I have N coils, each one has that area of the loop. I know what the magnetic field is because I have a formula right here. So negative AN times ddt of mu naught big N over L times I. And let's close parentheses. Mu sub naught's a constant. It's the permeability of whatever's in the core, which is air, which is close enough to 4 pi times 10 to the negative 7th. Capital N is the number of coils, L is the length of it. That's not changing. I run a current through this, I'm not suddenly changing the number of coils or the length of this thing. At least not appreciably. So this becomes negative A N squared mu naught over L times d I dt. Now, if you're dealing with an AC current, then that current, AC, then that current is oscillating back and forth. You got represented by a sine wave or a cosine wave, and so that definitely is changing the entire time. If you're dealing with DC, you've just got that brief moment from it's being off to being on until it reaches that steady state level. So in the lab, you're gonna do that. You'll have it set up, you'll turn it on, and you'll do a graph. And I think I asked for a linear graph of current versus time so you can get the slope off of it. But putting a more common form, u sub naught n squared A over L, and then a quick check to make sure I didn't do something silly there. Yep. Times d I dt. This right here, that is dependent upon the physical geometry of the solenoid. U sub naught's a constant, N is the number of coils squared, A is the area of the hole, L is the length of the solenoid, the distance from end to end, so this distance right there is lowercase l. And so this fraction here, which is dependent upon the geometry of it, is known as the inductance. And it is represented by the capital L. That's why I was reserving that one. And so my voltage in the direction of the current flow from the primary current flow is negative L d I dt.
Is that delta V sub L?
Where are you looking?
Yeah, delta V sub L.
Oh, yeah. So the voltage across an inductor. Just as a parallel, delta VR in the direction of current would be negative IR. Or RI. All right, questions here before we start using this slide? All right, let's use this stuff. Units of inductance is the Henry. I don't know why I'm capitalizing it, but anyway, technically it's a unit. Named after Big H Henry. The symbol for Henry is a capital H. And you've heard the trivia before. What is the reciprocal of a Henry?
Henry.
Or however it's supposed to be pronounced. So I got a battery here, hooked up to, I have an inductor. That's the symbol for an inductor, because an inductor, the inductance is caused by a loop of coils, and so we represent it by a loop of coils. And then I have a capacitor here. This will end up being the positive and the negative side of the capacitor as it charges up. Now recognize from a plotting point of view, as I start the battery, as I first connect the battery, I'm gonna have most back current initially from here. And then once the current reaches a steady state, this will do anything at all, because the inductor only has an effect when the current is changing. All right, so I have this set up, get the capacitor charged, and then I break the connection. And of course, that nice, ideal, perfect way. So what I have here is the LC circuit. I have a fully charged capacitor, which will then start to discharge because I have this path. So I have my electrons on the negative side will start to flow through the inductor to the positive side. So let's take a look at what the math looks like.
Wait, so LC circuits have a broken path?
It's just basically a fully charged capacitor with an inductor there. So in theory, I could start out with a fully charged conductor instead of going through the story of it's hooked to a battery initially. I could just start with a fully charged capacitor, take my inductor, connect it perfectly to the lead so there's no discharge into the air or anything like that, and let it rip. All right, so my current, I guess we need to establish that. My electrons are going to be flowing this way initially, and so I'll have my current, I'm just going to say it's flowing in that direction. I'm going to start my voltage loop here, and then I'm going to go in the same direction as I've defined my current. So I have voltage across the capacitor plus the voltage across my inductor is equal to 0. Kirchhoff's voltage loop rule. And this is Q over C minus L d I dt is equal to 0. Now, when we did the RC circuit, we had to be careful about, we have current coming off, we have charges coming off of the capacitor, creating the current. And so my current here deals with the charges that are going across the inductor, but that is the negative of the charges coming off of the capacitor. Because as the charges come off the capacitor, dq is a negative. Yeah, dq is a negative number because I'm losing charge here, but my current is positive, and so the minus sign sort of offsets that. So this is QC here. So I have QC over C minus L times, well, what is the definition of current? Well, I have it right there. This is negative, oops, try that again, times ddt of negative dqc dt. And again, QC is the charge that is on the capacitor. Equals 0. And so I have this Q over C divided by my capacitance plus L d squared Q dt squared is equal to 0. So I need some function for Q of C such that the second derivative is basically a negative of itself. And what function is basically a negative of itself? For example. I'll just do some generic A cosine omega t. So my first derivative with respect to time would be negative A omega cosine sine omega t. And the second derivative with respect to time, negative A omega squared cosine omega t. So plugging a formula here that will work for that second derivative, except I have this A here we need to deal with. So I have A over C cosine omega t plus minus L A omega squared cosine omega t equals 0. We get 1 over C minus L omega squared is equal to 0. 1 over C equals L omega squared. Omega squared is equal to 1 over LC. Omega is the square root of 1 over LC. And so we have a solution to this, or at least partial solution. The charge that is on the capacitor can be described by some amplitude times the cosine of 1 over the square root of LC. What is the implication? What's actually happening to the charge on the capacitor?
Increases and decreases.
Yep. So we got all this positive charge on one plate, it then flows through to the other side, and then it flows back, and then back, and it keeps going on forever. If only we could do that. Stupid resistance. So if I apply the charge, first time, charge on the capacitor. Basically, it's cosine curve there, or with resistance, it will eventually sort of peter out. I think it still maintains. Still peaks at the same time, I believe.
What would the A represent? The max charge?
A would be, yeah, it would have to be, because when time is 0, that's 1, and so we'd have QC is equal to A. So it's the charge. So we could think of that next step on Q's is not cosine. Likewise, we can do an LR circuit and basically the same similar process. Yeah, I was originally gonna do the LR circuit, but I'm just not in the mood right now. Unless you would like to do the LR circuit. And once again, you're just in awe. Ooh, I know what we should do next. Take a break. Stretch legs. I'm gonna pause this thing with the crazy notion that I will remember or someone will remind me. actually.